Now we had talked about separation techniques, and we had started figuring out different ways to separate substances. Mixtures were substances that are physically mixed and can be separated using physical methods by sand and water. Chemically, अगर mixed होते हैं ना, the properties change. When something physically mixes, the substance remain unique. You need sand and water. Sand still behaves as sand. Water still behaves as water. Uh, Now, how would you separate sand and water? You're going to filter it. Okay. In a large dam, what you're going to do, you're going to create a filter paper by rocks, by putting rocks together, so that the sand particles they get stuck in the rock particles, and pure water could pass through. Then there was another method called decanting, where you could allow the sand to settle because it's insoluble, and once it settles down, you can pour off the liquid from the top. That's decanting. Then we talked about suspensions. Suspensions
Can
are
you explain the depending?
hmm? Decanting was you had particles, sand and water are mixed together. Okay, so if they are mixed together, for example, muddy water, अगर आप उसको काफी देर तक रख लो, what happens? All the sand particles would settle at the bottom, right?
Yes.
So what you can do is you can tilt the container, and the water would pour off from the top, and the sand would remain behind. Is this clear?
You won't.
Uh, like what happens in muddy rivers is over time, when the water settles in a lake, all the sand and the mud, etc., it would eventually, all of it would settle at the bottom. And when it settles at the bottom, uh, the the water at the top would kind of be purified. It would be free of sand and mud, and you can sort of drink that water. Okay, is this clear? And then there was another thing which I discussed, and that was a suspension. A suspension is again a solid plus a solvent, an insoluble solid. But this time the solid particles are too fine. They're very, very fine, so they remain suspended. I mean, like muddy water. Why is muddy water? It looks as if the sand particles, the tiny sand particles, because they're so fine that they are spread out completely throughout the water, right? Uh, it's not like they are
Yes.
large particles. The whole water would appear muddy. So sometimes what happens is, to decant, especially a suspension, the particles would not settle at the bottom themselves. You want the particles to sort of settle at the bottom, right? But sometimes what would happen is that the particles are so fine that they're not settling at the bottom. So what you do is you use a centrifuge. A centrifuge is a device that spins very, very vigorously. So you put this test tube in that and you spin it. Uh, so what happens? Well, exactly वही होता है. Imagine you're in a car and the car turns. So what happens? All the particles would go in one direction, right? ठीक है. Imagine you sitting in a car and the car turns around. तो सारे लोग एक साइड पे नहीं जाते. So the same thing exactly happens with the particles over here. Okay, if I spin it, you put it in place and you start spinning it round and round. So all the particles would eventually go in one direction and they would all accumulate at the bottom, and you can decant it very easily then. Is this clear? So sometimes for decanting, you would need a centrifuge to sort of spin it vigorously so that all the particles they accumulate at one end and you can pour off the liquid at the other end. Then we did soluble solute like salt and water. Now this time the salt dissolves completely. Now when it dissolves completely, what happens is like I said originally, you have these salt crystals. Okay, for example, NaCl. These salt crystals, they're all attracted to each other. The positive ion and the negative ion are all attracted to each other. So positive attracts negative, negative attracts positive, and they're all attracted. What do? You start stirring it. When you stir it, all these salt particles they scatter, they dissociate. Okay, the word that's used is called dissociate. The tiny salt particles, because you're vigorously stirring it, so all these ions they start to dissociate, and the crystal breaks up, and the ions they start scattering everywhere in the solution, right? So all the Cl ions, and there are lots and lots of water molecules that are everywhere. ठीक है, Rafa, is this clear?
Yes, sir, it is.
Achha, this is how a salt dissolves, or pretty much any substance dissolves. This is just one example. Now, the thing is, why don't they get back together again? The reason they're not able to get back together again is because there's so many water molecules in between that the water molecules are not going to allow them to join together. It's a very dilute solution. Dilute solution where there's a lot of water. So there are billions and billions of water molecules in between the sodium ions and the Cl ions that they can't get back together again. So one way to get the crystal back again is like they've dissolved now. Okay? One way to get the crystal back again is you get rid of the water. So what you're going to do is you start heating this. I mean, this is the dish given, and you start heating this container strongly. So slowly, all the water molecules they evaporate. And if and when you're evaporating, you do it very quickly. There's strong heating involved. When you evaporate them, the sodium ions and the Cl ions might, because now the water molecules are out of the place. I mean, they were previously in between the ions, but now they're no longer together. So what's going to happen is that the ions would get back together again, and the crystals would form. Right? Is this clear? So the simple process is evaporate everything, evaporate
Yes, sir.
all the water. The problem with this is that it would not give you large crystals. I mean, you're going to get very small, tiny crystals. The reason is because you're evaporating water so very quickly that they don't get enough time to sort of rearrange themselves. For example, they can't really form a big crystal. Water evaporated at that end. So you only get this powdered sort of crystals, very fine powdered crystals. Imagine a salt solution and you're evaporating it very strongly. So large crystals are not obtained as water leaves the container quickly and not enough time given to ions to form the lattice. And impurities would be a part of the tiny crystals. Now you imagine these tiny crystals, like tiny microscopic crystals. For you, they appear to be as if they're in powdered form. Now, the container would have a lot of impurities as well. So, let's say there are sand particles everywhere. Now, those tiny crystals, sand is going to be a part of those tiny crystals. I mean, a lot of impurities would be present. So, it's not a very good way of obtaining crystals. Reason is number one, you're not going to get big crystals. Number two, the crystals would be contaminated by other impurities as well. So, Rafa, is this clear?
Yes, sir.
I said a better method is crystallization. Now, the only difference in crystallization is that when you crystallize a substance, same situation, that you have, it's the same situation. You have Na plus one and you have Cl minus one all scattered in the solution. Now, in this case, what you do is you don't evaporate the solution to saturation. You evaporate the solution to saturation point. So instead, what you do is, like initially, there's a lot of water molecules. The black ones are your impurities. So initially, you have a lot of water molecules. Now, you don't get rid of all the water molecules at once. You evaporate some of them, right? Not a lot, but you evaporate some of them. Uh, so the ions can sort of still swim around. I mean, there's still enough water, but the quantity of water is lesser. Now, the next part is you cool the whole thing gradually. Once you've evaporated the solution up to a certain point, up to the saturation point. Saturation point is the point where there's not enough water left. So what happens is that the sodium ions would slowly swim around and they might meet the sea lines. Now the chances of them getting together is more because you don't have a lot of water molecules in the way. And so slowly, when you cool them gradually, there would be chances that the sodium ion would swim and come close to the Cl line and would get attracted to it. The Cl line would swim around and might get attracted to the sodium ion, and a larger crystal would be formed. If you do the cooling process very gradually, you're going to allow them the time for them to arrange themselves. Okay, Rafa, is this clear? So now in this way you get you filter out the crystals formed, and in this way large crystals are formed. So you're not getting the powdered substance like in the first place. Small tiny crystals were forming everywhere because you were getting rid of the water very, very quickly. Now what's happening is you're getting very large crystals. And these large crystals are easy to identify. I mean, you can easily pick them up. You get very large, beautiful crystals. And one example is I can show you some images like a CuSO4 crystal. So you can see, so you can see these large, very large crystals that can form. Uh, I said, now the good thing about these crystals is they're very pure, and you can sort of pick them up very easily. So just one second. So you can pick them out very easily, and the impurities, even the impurities, would be left behind because it's very easy to identify the large crystal. अब a simple distillation किया था कि if you don't want the salt, if you want the water, what do? You heat it, the water evaporates, cools at the other end. Over here, there's a condenser, and the water molecules lose energy. This is known as the distillate, and the salt remains behind. As I'm going to इसका तो video आप देख लेना complete. I'm going to move forward from this point onwards. We're going to study another separation technique, and in this case, we're going to study. So what we're going to study is two miscible liquids, a mixture of two miscible liquids. Now, the first thing is, what are miscible liquids? Miscible liquids are that liquids that mix with each other, and two or more. It could be more than two as well. So these are liquids that mix with each other or soluble in each other. I mean, they're not going to form separate layers like oil and water. Oil and water are immiscible liquids. These are miscible liquids. Now, the way to separate miscible liquids is the method is known as fractional distillation. Now, fractional distillation is I said it's fractional distillation. And fractional distillation uses what property to separate them? It uses the different liquids have different boiling points. So you have different liquids having different boiling points. Only then can the liquids be separated, and they have to be miscible. Only then would you use fractional distillation. So the diagram would be that you have a boiling flask. So let's quickly make make a round bottom flask, and that flask is where the two liquids would be present, mixed together. Uh, Example of such liquids is ethanol plus water. They both have different boiling points, 78 degrees centigrade, and this one is 100-degree centigrade. So they both boil at different temperatures. Now, on top of this round bottom flask, you have a fractionating column. Okay, so I'm going to make a fractionating column now. So you have a fractionating column, and the fractionating column would be attached to the opening of the container. Okay, so there's this fractionating column, and that fractionating column has lots and lots of glass beads, or it could be anything that increases the surface area. So there are plenty of glass beads over here in this fractionating column. And the top is connected to a condenser. So right at the top you have this condenser, and the condenser is basically a water jacket that has water in and water out. Okay, that's your condenser, and that's pretty much your diagram. I'm going to put a stopper at the top, and there's going to be a thermometer at the top as well, right at the opening. So this is your entire diagram. You might be asked to draw this entire diagram. Let's label this. You're definitely asked to label this. So this one is your fractionating column. This is obviously your condenser. This is water in, and the other side is water out. The purpose of a condenser is to cool the vapor. And over here, there's going to be this small beaker where you're going to collect the distillate. So this over here is where the distillate is collected. Now, what happens is you're going to heat this mixture very strongly. So there's going to be heat applied. Now, the first thing that would happen is, let's say there are all sorts of molecules. These are ethanol molecules, the pink ones, and you have the green ones are water molecules. Quickly answer, which one is going to evaporate first, ethanol or water? If you start heating,
Ethanol.
okay, so ethanol, because it has a lower boiling point. So that's the first thing. Lower boiling point liquid boils and evaporates first. And the rest is simple. So you have this. So I'm going to pick a ethanol molecule, and it's going to go from this point. It would bump into these glass beads. Eventually, it's going to escape and into this tube over here. And from that tube, it's going to lose energy, and it's going to condense and fall in the distillate as a liquid molecule. So one by one, not one by one, I mean, lots of ethanol vapors are going to pump into these glass beads. They're going to travel through the container, and they're going to fall over here. So this would continuously happen. And eventually, the distillate is going to be comprised of the lower boiling point liquid. This side is the first thing that you're going to obtain over here is the lower boiling point liquid. अच्छा, can anyone tell me what's the purpose of adding these glass beads? मतलब ये molecule जो है ये तो वैसे भी जा सकता था. I mean, it can. मतलब why don't put the condenser? Why make it collide with all these glass beads and then send it to the condenser so that it condenses? Any ideas? So the thing is, okay, let's say the temperature is 78 at the moment. Okay, initially you're heating the substance and the temperature is right now 78 degrees centigrade. So it's obviously the pink molecules that would be changing state because ethanol has a boiling point of 78. But can water evaporate at 78? Or मुझे बस clearly ये बता दो कि does water have a specific मतलब can it evaporate at 10 degrees centigrade? Anyone, Rafiq?
No.
नहीं, अगर जमीन पे पानी फेंको, what happens? Does it evaporate?
Yes.
ठीक है, so remember this. Boiling, there's a difference between boiling and evaporation. Boiling happens at a fixed temperature. ठीक है, what is boiling? Boiling happens at a fixed temperature. दोनों का मतलब एक ही है. दोनों में क्या होता है? Liquid changes into gas. Pretty much the same happens in evaporation as well. A liquid would change into gas. But remember, boiling happens at a fixed temperature. When you talk about boiling, uska matlab hai कि the whole liquid as a whole is basically trying to change state. ठीक है? For example, there's a pot full of water that's boiling. तो उसके अंदर every part of that liquid is trying to change state. Evaporation में क्या होता है कि evaporation में there might be just a few molecules that might, for example, ये वाला ऊपर घूम रहा है, ठीक है? ये जो top पे. Evaporation में what happens is there might be a single molecule of water that might gain, due to collisions, might gain energy, और वो top surface से ना escape कर जाते हैं यहाँ पे. ठीक है? So do you get the idea of evaporation? कि evaporation के अंदर it's not that all the molecules are trying to evaporate. Evaporation is when just a few random top surface molecules might gain energy and they might escape as a vapor. So is this clear, Javeria, Rafe? Acha, so the problem would be that you were expecting all the ethanol at 78 degrees centigrade, you were expecting all the ethanol molecules to evaporate and change state. So you were expecting this, that all the ethanol molecules at 78 would change state and they would sort of move into the condenser. But there would be very few water molecules that are going to contaminate the mixture. Just a few. Like some random water molecule might gain energy and might escape the surface of the container. And the thing with that single random water molecule is that when it reaches the glass beads, it's going to hit the glass beads and it would start colliding with them. And when it collides with them, it loses energy. And when it loses energy, it's going to condense and it's going to fall back into the container. Do you get this part? That a random water molecule might escape, and but when it reaches the glass piece, there's so many collisions happening that it starts to lose energy. And when it loses energy, it condenses and it falls back. So the glass beads are like a barrier that they they I mean they force the vapor to into so many collisions that only the ones which are already gaseous at 78, only they would maintain their gaseous state. Any other random molecule whose boiling point is not 78, and if it by any chance escapes as a vapor, it would lose energy and it would fall back into the container. So the particles that are reaching over here, they would only be, I mean, the particles that are reaching the condenser would be the low boiling point particles. Any of the green molecules, they would just fall back. So is this clear? So I'm going to write this down. Okay, this is going to be the explanation for the fractionating column. Why do we need a fractionating column? And the answer is, let's write the answer first and the description. So the fractionating column increases the surface area. So it increases the surface area so the particle would have more collisions. So high boiling point vapors that would be formed, but in a very small quantity, high boiling point vapors would lose energy due to collisions and will condense. Hence, pure distillate would be obtained. So their main purpose is, it's this one. A fractionating column increases the surface area to prevent the high boiling point liquids from reaching the other end. So only those particles would reach the other end, which are going to be gaseous anyways at 78 degrees centigrade. And that's where you're going to that's why you're going to get a pure substance at the other end. I said, now tell me one more thing, which is, I said, even how would you know ethanol, all of the ethanol has evaporated and you have collected it over here? Any idea, Javeria? Any idea?
The water out will not come anymore.
Nee, but how would you know? I mean, that's where the thermometer comes in. Okay, the thermometer is going to tell you 78 was the boiling point of ethanol. So if ethanol is boiling, the temperature would remain 78. Boiling happens at a fixed temperature. Once all the ethanol, every single particle of ethanol is has reached the other end. Okay, let's get rid of all the ethanol. They've traveled and they've reached the other end. Uh, Now, what is in your container and which thing would boil next and at what temperature? Okay, once this is done, now your container only has water and water has a boiling point of 100 degrees centigrade. So the temperature would start to rise and would now become constant at 100 degrees centigrade because the water molecules are evaporating. So is this clear? Ajay, so I'm going to make a graph of what the temperature readings would show in this case. That they're going to show this is the time or progress of the reaction. So initially, you're going to start at room temperature. Uh, the temperature would increase, but then it would become constant at 78. And once all the ethanol evaporates, then it would become constant at 100. And after that, the temperature just keeps on increasing. So the first thing is the graph is going to look like this. That let's say you're starting at room temperature, you started to heat this container. It becomes constant at 78 degrees centigrade. That indicates that ethanol is boiling and it changes from liquid to gas. At this point, all the ethanol has this particular point. All the ethanol has evaporated. Now your container has water in it. So at 100 degrees centigrade, it's water's turn now. So now water has started to boil, and the temperature would remain fixed at 100 degrees centigrade. And once water has boiled, then it's simply the temperature just keeps on increasing. I mean, that's basically the point where you have to stop the heating because your distillation is over now. So remember this graph as well. Remember all the tiny details, especially where you're going to put the thermometer because it's always put at the opening of this condenser. So is this clear for everyone now? I'll just quickly explain. Okay, why doesn't temperature rise when the state changes? The thing is, okay, imagine um, imagine there's a liquid, right? Now in a liquid, and let's imagine there are just four particles in a liquid. Okay, let's make more. Take 6, 7 particles. Now in a liquid, the particles are kind of strongly attracted to each other, but not that strongly, so that the particles are sliding past each other. Uh, so there is attraction, but they can't move freely. Now, when you give a substance energy, energy does two things. Whenever you heat a substance, two things happen. Either what happens is that kinetic energy increases. I mean, that is usually what happens. That is usually what happens. Kinetic energy increase करने का क्या मतलब है? The particles they start to slide and slide more vigorously, right? I mean, that is what is meant by kinetic energy. That the particles they start to move more vigorously, but it's still liquid state. मतलब पानी को 10 डिग्री सेंटीग्रेड पे देखो, पानी को 60 डिग्री सेंटीग्रेड पे देखो, दोनों स्टेट्स में क्या फर्क है? It's still liquid. The only thing is that the kinetic energy is higher, and the kinetic energy is basically your temperature. I mean, your temperature measures kinetic energy. ठीक है? Is this clear? This first part. Okay, when you give a substance, particles they start to move more vigorously, and their kinetic energy increases. ठीक है? Is that part clear? Yes or no?
Yes.
Yes.
Achha, but then at a certain level, if the particles gain enough kinetic energy, what would happen also is that at a certain point, like for water that's 100 degrees centigrade, that energy would be used to break the bonds or break intermolecular forces. So at a certain temperature, there would come a point when the particles they gain enough energy that they start to break the bonds. and the molecules they escape as gas. So all these molecules they kind of turn into gas and they fly away. Okay? In gases, the particles are moving freely in all directions. So they randomly fly away in all directions. So this is what happens when bonds break. The forces that were keeping that were keeping the particles together, they have now been broken. Okay? Is this clear?
Yes, sir.
So I'll just reiterate okay, why the temperature becomes fixed. Because during change of state, energy is used to break bonds, whatever bonds they are. It's used for breaking of bonds, which is why kinetic energy remains constant. And kinetic energy is basically your temperature. So it kind of remains constant when boiling is happening. So remember this diagram over here. Okay, what is fractional distillation and how does it work? You're going to be asked questions about the diagram as well, and you're going to be asked questions about the fractionating column, about the whole apparatus, labeling it. Now, there's one application of fractional distillation, and uh, that's a huge application, and we are going to study it with this. That is fractional distillation of crude oil. That is an industrial application, fractional distillation of as a fractional distillation of crude oil. Now, first thing, I'll just we don't have much time right now, so I'm just going to first describe what crude oil is. Does anyone have any idea what crude oil is? मतलब what type of oil is this? मतलब real world में where would
It is a fossil fuel.
ठीक है लेकिन real world में crude oil कौन सा it's the raw form of oil that you get from the oil wells. So crude oil is जो refine not through refineries जो for example let's say Saudi Arabia के अंदर there are oil wells तो वहां से underground oil that's called crude oil. ठीक है crude means the rough form of oil. अच्छा now it's a mixture of many different fractions. अच्छा वो जो components हैं ना they're known as fractions. So it's a mixture of many different fractions. अच्छा this is going to be very important. ये जो अभी हम पढ़ रहे हैं ना you get very large questions on this. Uh, Small questions as well, like you get very big questions on this as well. So it's a mixture of many different fractions. Fractions का मतलब है components. Like many different liquids could be mixed together. अच्छा now you get अच्छा the purpose of crude oil is humans usually use it for power as a form of energy. They use it to convert to actually produce energy. अच्छा सबसे पहले what different fractions you have gases, petroleum gases in it, like methane that you get at your homes. Then there is gasoline, which is known as petrol. That's that's used in as a methane is used in domestic heating. Gasoline is used in cars. You have naphtha, which is used as a feedstock for chemical industry. So it's used in the chemical industry for making medicines. You have kerosene. This is known as airplane fuel. So you must know each and every use. You also get, apart from kerosene, you get furnace oil or fuel oils. That's for your furnaces. You also get diesel from it, which is used for heavy transportation, trucks, etc., even ships. Now, from that mixture that you're getting from the earth, you also extract lubricating fractions. ठीक है, for example, waxes and jellies और ये creams वगैरह भी ना उसी से बनती है. Polish, car polish. So there's some other substances. Bitumen is present, which is the black tar that you see on your roads. That's for making roads. So the point is, पिछला जो केस था, पिछले केस में your container had just two mixtures, ethanol and water. Crude oil is slightly more complicated. Crude oil is a mixture of many different fractions. All have different boiling points. Petroleum gases, gasoline, naphtha, kerosene, fuel oil, diesel, lubricating fractions, and bitumen. You must know all the uses as well. Okay, you get very big questions on the individual uses. So remember the individual uses of each of the components of crude oil. Now, in the next class, we're going to learn how to separate them into different fractions. How, like we did in the previous case. The whole concept is exactly the same. That the lower boiling point substance would boil or evaporate first, and you're going to collect it. So the substance that has the lowest out of these mixture, I mean this entire mixture, the substance that has the lowest boiling point is going to be evaporating first, and you can collect it. And the substance having higher boiling points would be evaporating later, and you're going to collect them later as well. तो यहाँ से हम कंटिन्यू करेंगे. Any questions about this?
No, sir.
ठीक है, Javeria, any questions?
No, sir.
ठीक है, so we can continue with this tomorrow then, in tomorrow's class. ठीक है, चलें. Okay, take
Sir,
care.
will you have class on Friday?
हाँ, yes, we will have class on Friday. ठीक है, चलें. Okay, take care. अल्लाह हाफिज.